Test, test. All right, good evening, everyone. Welcome to the Leitner Observatory Public Night. It's Tuesday night, time for a public night yet again, not from the Leitner Observatory, but from my house in Hamden, Connecticut. I am Michael Faison. I'm the director of the Leitner Observatory and Planetarium. I often present shows on Tuesday nights, although often we have our student presenters doing them. Sometimes we have guest lectures on Tuesday nights as well. And tonight, instead of a recorded planetarium show, what I thought I would do is interview or chat with one of the scientists, one of our grad students who had a nice press release recently about detecting the atmosphere, the composition of an atmosphere of an exoplanet. So after I do my presentation of what's up in the sky tonight, we're going to talk to Sam Cabot about this amazing discovery of metals in the atmosphere of a distant exoplanet. It's pretty clear tonight, not perfectly clear, but if we were at the Leitner Observatory, we would certainly have the telescope set up for public viewing tonight. I think it's clear enough to see some things. I'm in my home office at the moment, and you can see above me is a telescope as seen from my security camera outside. So we'll see if we can actually do some live observing. This telescope is a little bit fancier than the amateur equipment that I had set up last Tuesday for the live stream. I managed to sneak into the Leitner Observatory last Saturday to grab some equipment quickly. So I've got some nicer equipment this week. It was a beautiful day on Saturday. This was the day when all the New Yorkers were out, supposedly not social distancing. It was a beautiful day here as well, and I was out at the Leitner Observatory cleaning up and grabbing some equipment, including this telescope mount and telescope. But a lot of people were out enjoying the sunshine in the park around the observatory, but they seem to be doing a good job of staying away from each other. So good job New Havenites avoiding each other on a nice day. It's not quite dark here in New Haven, which is another issue with live streaming at this time. Last week, I had the moon almost directly overhead, and I had the, Venus in the trees. And this telescope is actually on a remote robotic mount. So if I actually switch over here to my telescope control, you can see I've got the the video of the telescope and then a control window that will allow me to move the telescope and potentially take pictures. So a little bit later when it gets darker, one thing I'm going to have to do is run outside and potentially point the telescope at a calibration star so the computer knows where it's pointed in the sky. This is an old telescope mount and an old telescope, and so it may well break. It was clear last night, and I had some trouble with the telescope and had to get a soldering iron to do some repairs. I've done lots of repairs on this telescope now. Maybe it's about time for us to replace it. So we'll see how it goes. I'm not going to spend an infinite amount of time trying to point the telescope at stuff. I can show you some of the images that I took last night when I was doing my tests. So another idea of the view that we get from New Haven of some of these interesting objects in the sky. First thing that I want to do is just give you a quick preview of what's up in the sky using this simulator. So I'm going to turn off my telescope cam out there, and I'm going to jump over to this simulator program. So this is still Stellarium, and you can still get this software for free. So let me demo that. Let me talk about that quickly. So if you go to stellarium.org, you can download this software for free for your Mac or Windows computer or Linux computer or whatever. And it allows you to simulate the sky from anywhere at any time see what the sky looked like on your birthday, see what the sky looked like the night of the Titanic disaster. That's actually doing that kind of historical astronomy. It's kind of a fun thing to do with these planetarium simulators. But it's great for education, great for planning your observing sessions. Also, it's May, and there's a new sky map out. So I mentioned this 2 weeks ago. There's a great resource, the skymaps.com, will publish a new sky map showing what constellations are out and where the planets are relative to the constellations each month. So if you look at the sky map for May 2020, you can see some events. So we actually have had some astronomy events recently. So May 1st, for example, May Day, Beltane, is an astronomically based holiday. It's actually midway between the winter solstice and the, it's midway between the spring equinox on March 21st and the summer solstice. So all of the sort of pagan traditional Celtic holidays are based on an 8 octant of the year, going from the spring equinox to the summer solstice, to the fall equinox, and so forth, all the way around, and then halfway in between those. So May 1st, May Day, was midway between them. Also, you see this on the sky map. There was another annual meteor shower recently. Actually, today was the peak. Early this morning was the peak. If you want to see some meteors, you have a chance of seeing meteors tonight after midnight. It's not so great tonight because the moon is close to full. So when you have one of these annual meteor showers, especially not a very bright one, the phase of the moon matters a lot. If you have a full moon or a last quarter moon, it's going to make the sky quite bright, and it's harder to see the fainter meteors. One thing that's neat, though, about the Eta Aquariid meteor showers is that the particles that are burning up in the atmosphere come from Halley's Comet. So famous comet. And the Earth is actually passing through part of the orbit of Halley's Comet. And there are all these, there's a stream of small dusty particles left over from the last time the comet went by in 1986. And those will hit the Earth's atmosphere and burn up. And you can expect to see about 40 meteors per hour for that meteor shower. Let's see, I don't think there are any other interesting kind of planetary events happening for the rest of the month. Jupiter and Saturn are getting higher in the sky as the Earth orbits kind of between Jupiter and Saturn. Actually, a couple of weeks ago, someone asked me what I meant by Venus being retrograde. And so I was thinking maybe I would talk about that next week, what it means to say that Venus is retrograde. This is something that happens from our point of view when the planets appear to move backwards relative to the stars. And I think this actually starts next week for Venus. So this is a view of the solar system from above, looking down from the North Pole. And so you see where the Earth is right there, where Venus is right there, kind of a little bit to the side of the sun, not quite in line with the sun, but getting closer to the Earth. Mars is over here in the morning sky, Jupiter is over here in the morning sky, and then Mercury right here is basically in line with the sun. So when Venus goes between the Earth and the sun, it goes retrograde. So maybe I'll try and talk a little bit about what that actually means. Actually, I had some other astronomy news. Last week we were looking at the moon, and someone on the live chat asked me, do we ever see new craters on the moon? And we do. And I saw this news article pop up on space.com today. The hunt for asteroid impacts on the moon heats up with a new observatory. So this is a dedicated observatory looking for flashes of light, usually on the dark side of the moon, indicating something hitting the moon. And it happens actually quite often, more often than I realized. Although if you have a big telescope, you can see these things happen more often. A neat thing about asteroids or meteoroids hitting the moon, because the moon has no atmosphere, much smaller particles will come down and hit the moon. The moon is hit by stuff just as often as the Earth is, basically. The moon and the Earth are at essentially the same place in the solar system relative to each other. So if you have a big enough telescope that's monitoring the moon often enough, you'll see these little flashes of light that indicate vaporization of meteorites hitting the surface of the moon. And that's actually interesting to study. Anyway, let's go back to the simulator and I'll talk about what's up in the sky tonight. So let me bring Stellarium back up here. Okay, so what I'm going to talk about, by the way, if anyone has any questions in real time about what I'm talking about, or any questions about anything in astronomy or astronomy news or telescopes or anything like that, feel free to type them in the YouTube live chat. I'll keep an eye on that and try to remember to answer your questions. Okay, so let's look at the sky tonight in the simulator. So sun's going down. It's about 7:45. Let's run time forward a little bit, as seen here in New Haven. We got about 8 o'clock, about 8:30, and then about 9 o'clock. So Venus is getting quite low in the western sky. It's getting harder and harder to see at sunset as it goes between the Earth and the Sun in its orbit. And we've basically lost the winter constellations. So if you're looking for Orion or Taurus, even Gemini is getting very low at sunset in the west. So winter constellations are done. We're basically on to the good summer constellations. So a lot of these I talked about last week. I'll just mention some of these again, the ones that are bright enough to see from the city, and then I'll point out a few other interesting things. As usual, I think it's best to start with the Big Dipper. The Big Dipper is quite bright and easy to see even when you've got a lot of light pollution. So I'm going to swing the sky around so that we're facing more or less north, a little bit northeast. And these 7 stars are the stars in the Big Dipper, which are part of a much bigger constellation of Ursa Major, the Big Bear. So if you use the 2 stars at the end of the cup, they will point to Polaris, the North Star, like so. And if you use the handle of the Big Dipper, we say that you can arc to Arcturus, like so. So Arcturus is a bright red star. It's actually a red giant, about 100 times bigger than the Sun. It's also fairly close to us. It's only about 30 light years away, so it's quite close, especially for a red giant like this. Anyway, so we arc to Arcturus. There it is in the constellation of Bootes, the herdsman. If you continue on, you will spy Spica, which is the brightest star in Virgo. Once you have Spica, since Spica is in Virgo, that helps you find the zodiac. So the zodiac is made up of constellations that are along the ecliptic, which is the plane of the solar system. So that image I showed you a second ago of the orientation of the planets relative to each other, they're orbiting in more or less the same plane that the Earth orbits the Sun. And so we always see the naked eye planets and the Sun and the Moon close to the ecliptic in the sky. So we always see the Sun and the naked eye planets and the Moon, those 7 planetary objects that move around relative to the stars, close to a zodiac constellation, or in a zodiac constellation. So the Moon tonight is in Virgo. If we were to look tomorrow night, it will move over to almost to Libra. The night before, it was closer to Leo. If we go back 3 nights, it was in Leo. And so we can use these constellations to keep track of the position of the Sun and the Moon and the naked eye planets. If you use the Big Dipper to go the other way, so these 2 stars in the cup point to Polaris, the North Star, over there, which is always due north no matter what time of night, no matter what season of the year. If you go to the other 2 stars in the cup and go the other way, they will take you to the bright star Regulus, which is the brightest star in Leo the Lion. Now, Regulus is almost right on top of the ecliptic. I can zoom in a little bit on it. Zoom in a little bit to show you. So it's very close to the ecliptic, and in fact sometimes the Moon and the planets will get very close to Regulus, and in fact sometimes the Moon will cover Regulus, and we call that an occultation. And that's actually very useful for lots of things, lots of interesting astronomy you can do when the Moon occults a star. You can study the orbit of the Moon very precisely, but you can also use it to study the star very precisely because of the way the light blinks out. So interesting opportunity to study these stars. Let's see if there are any other interesting constellations or targets I want to point out. Looking over here in the east at 9 o'clock, I can see some of the late spring constellations coming up, such as Libra, the scales, and Ophiuchus, the snake handler. I'll go a little bit later in the evening. And actually, we don't have to go too late before we would see Jupiter and Saturn rising. I think we'd have to go to about 1 a.m. or 2 a.m. or so to see them. But here we are at about 1 a.m. Eastern Daylight Time. And so we can see Libra, we can see Scorpius, which I think of as a summer constellation. If anyone's been to my planetarium shows recently, you know that the two bright stars in Libra have some of my favorite star names. This is Zubanesh Shimali, and this is Zubanel Ganubi. So Zubanesh Shimali is Arabic for the northern claw, and Zubanel Ganubi is Arabic for the southern claw. And in fact, these stars used to be part of the constellation of Scorpius, where Antares was the heart of Scorpius. You see core Scorpii there, the heart of Scorpius. And these were the claws. And at some point, an astronomer chopped them off and made them into a set of scales, Libra the scales, which are the only non-animal, non-human constellations in the zodiac. Right? The word zodiac comes from zoo. The same root as zoo, zoology, and so forth. It's a collection of animals, but Libra is the only thing in there that's not an animal. Let's go back to a little bit after sunset. Let's go back to about 9 o'clock. And I'll point out a couple of things you could see tonight with binoculars, if you have binoculars, or with a small telescope, if you've got a small telescope. Maybe if we were doing public observing at Leitner, we would look at some of these objects. So let me hide the ecliptic as well, so it's a little bit easier to see these stars. Once you find Spica and once you find Regulus, that helps you find the zodiac, and any naked eye planets will be close to that line, right? There is Venus over in the direction of Taurus. There's the moon over there in the direction of Virgo. So Regulus, then if you sort of follow Spica and Regulus around, you can find the bright stars in Gemini. So we've got Pollux and Castor, the two bright stars in Gemini. Bright stars, you can see them anywhere, even if there's light pollution. You can see these bright stars. These can help you find the Milky Way. So kind of at the foot of Gemini is where the Milky Way is. So the Milky Way is quite low in the sky tonight at sunset. That's just a consequence of my latitude right now and the season that we're in right now. In the sort of early spring, late winter, the Milky Way is much higher in the sky. And then it happens again in the fall when the Milky Way is quite high in the sky at sunset. So even if we didn't have a lot of light pollution in the city and a nearly full moon tonight, it'd be hard to see the Milky Way because it's so low down there. By the way, about the moon, it's not quite full. There's the moon over there. You can zoom in on a little bit and take a look at its phase. So I think we have a full moon on Thursday. So we're 2 days shy of a full moon. So it's about 97% illuminated tonight. Anyway, objects you might be able to see with your binoculars. Well, a great place to start if you're interested in finding interesting things with binoculars, besides, of course, looking at the moon and any bright planets that are out. You can look for Messier objects, M objects. So one example that I've talked about a couple of times is the Beehive cluster, M44. And this is a great target because it's big, it's bright, it's right in the middle of Cancer. You can see it very clearly with binoculars, and if you have a small telescope, you'll get a great view from a small telescope. Let me see, there's a question. Have we tracked ejecta from meteor impacts on the moon that then fell to Earth, tracking a specific event end to end? And how often do we recover moon ejecta on the Earth, chunks that survive the atmosphere? That's a great question. Believe it or not, we do have pieces of the moon here on Earth that were not brought back by Apollo astronauts. By studying the composition of meteorites, we can often figure out where they came from. Sometimes we can figure out exactly what asteroid it came from. One of the brightest asteroids in the sky is called Vesta. It's quite a big asteroid. And we've had a spacecraft orbiting Vesta, the Dawn spacecraft, returning these high-resolution images for a while. So if you go search Dawn Vesta, you can find some nice images. But actually, a lot of meteorites that we find on the surface of the Earth come from Vesta. Vesta was smacked by something at some point in the history of the solar system, and bits of it were strewn across the asteroid belt, and then over hundreds of millions of years, even billions of years, bits of them fell to the Earth, and so we can actually find pieces of Vesta. I have a piece of Vesta in my office. I've got a meteorite, which is actually a Vesta-type meteorite. They're not that rare, so I will use it when I teach about asteroids, but I don't have it here. Anyway, about the moon, we do have pieces of the moon that were knocked off the moon by an asteroid impact, orbited around in the solar system for a while, fell to the Earth. We found them, and we know that they came from the moon based on their chemical composition, especially the isotopes that are in the moon rocks. So, do we know of any specific? Have we ever recovered any moon ejecta specifically attached to a specific event end to end? I don't think so. I would be very surprised. I don't know of any. I could look into that and see if that's true, but I would be very surprised because the chance of a piece of rock on the moon getting escape velocity and heading out there into interplanetary space and then falling on the Earth and then surviving and being discovered are very, very, very small. So I don't know of anything like that. Anyway, back to my simulator. So good question there. Back to my simulator. So I looked at the Beehive cluster last Tuesday when it was clear with my telescope, and I thought I would show you a picture that I took last week with my little 90mm refractor. So let me bring up my browser window here so I can show you that picture. Here we go. So this is a picture that I took with a Canon SLR camera through that little blue Meade 90mm refractor that cost me $150. So I was trying to make a point last week that you can get into astronomy without spending a ton of money. This is about a 5-minute effective exposure with a $200 camera through a $150 telescope using a $300 mount. Now that adds up to not an insignificant amount of money. And you can do astrophotography, you can do visual observations and astrophotography for much, much cheaper. But still, I was really happy with this. Now, if I zoom in on it, you'll see some flaws. You can see the stars aren't perfectly round. There's a little bit of focus softness and a little bit of tracking error. But another nice thing is that you can see the colors really clearly. So you can see that many of the bright stars in this image are bluish. And that's very common for open star clusters, especially the ones that are close and the ones that are down here in the plane of the Milky Way with us. This is a star cluster that's fairly close to the plane of the Milky Way. So we can actually figure out how old this star cluster is and how far away it is. I think this one's about 100 million years old, a little bit less than that. And we know that because these blue stars are very massive. And we know that massive stars don't live for very long. They actually die. They go supernova and the cores collapse. So this star cluster is relatively young, but it makes for these really pretty, nice blue stars. Now, I also last night took a picture of the star cluster with the telescope that's outside right now that I have set up. It's a bigger telescope. It's an 8-inch refractor. And this is the same star cluster, but zoomed in quite a bit. So if you see this little house-shaped pattern of stars, and that little triangle of stars, that little triangle of stars, that's the same as this little house-shaped pattern of stars, and that little triangle, that little triangle. So I have not had time to go in and properly calibrate the images and combine them and do all the things that would make for a nice picture. I just got the pictures last night and threw them up, so a little bit more work that I can do to make the images look better. Anyway, back to the simulator. Let's see. And, oh, I don't want to hide. Let me bring myself up here. There I am. Okay. Another nice object that you can see, it's less easy with binoculars, but you can see it with a small telescope. And this is one of my favorite things to look at in the spring and even in the winter, is this double star right here in Cancer. So it's drifting off because the simulator is matching the rotation of the sky. So let me pause time so that it doesn't drift off. So this is a star. You see it has an Arabic name there, but I know it as Iota Cancri. And it's actually a binary star system. So two stars orbiting around each other. And let me show you this. Let me show you this one. I also took a picture of this star through the telescope last night. And if we have clear skies a little bit later on, and I can manage to get the telescope focused in a line, maybe we'll actually look at this one. But this is a picture of Iota Cancri from my backyard last night. And you notice anything about the two stars? Are they exactly the same? Looks like one is maybe a little bit bigger than the other. I'll zoom in a little bit here. And they don't quite have the same color cast, right? I think that one's a little bit orangish white, and that one's a little bit bluish white. So for stars, blue stars are hot, and red stars are cool. To an astronomer, red star means cool, or red means cool, blue means hot. Right, so when an astronomer goes to the tap and they want hot water, they turn the blue colored tap, and it doesn't make any sense that cold water comes out because blue is hot and red is cold. Anyway, these two stars are orbiting around each other, around their common center of mass. And this one is smaller and hotter. This one is much bigger. This is probably a red giant star, and so it's cooler but much more luminous. And when you look at it through the telescope, you can really see that very clearly. You need a little bit more magnification than you get from binoculars, so this isn't a great binocular object. I'll show you one more, actually I'll show you two more of these star clusters. So we'll zoom back out, and we'll look over here in the direction of sort of the left claw or the south claw of Cancer. There's this thing you see, it's called in Stellarium the Golden Eye Cluster. So we called this, the Messier name for this is M67. Let me zoom in on it here. All right, boy, that's a boring star. I mean, compare that to the Beehive. The Beehive is big and bright and beautiful. This little tiny thing, Golden Eye Cluster, what are you talking about? This star cluster is much, much further away, and it's actually made up of much older stars. So let me show you the picture that I took of this one. So I will switch back to here. Okay, so this is a picture from the 8-inch telescope in my backyard last night using my Canon DSLR, effectively a 20-second exposure. And yes, you can see it's smaller and dimmer, but I still got a decent picture. If I zoom in, it looks like the focus was a little bit better, but now you can really see the background noise that's inherent from using an uncooled commercial amateur digital camera like this. I mean, professional astronomers use cameras that are cooled with liquid nitrogen to very cold temperatures, and you take long exposures and so forth. But again, I haven't really done the proper calibrations to make this image look good. But you can really see that the brighter stars in M67 have kind of a reddish tint, versus the brighter stars in M44 have kind of a bluish tint. And this is the main way that astronomers learn about the ages of stars. Looking for stars in star clusters and looking for the oldest stars in the star cluster. These reddish stars are red giant stars at the end of their lifespan as normal stars. So another nice target to look at through a medium-sized telescope. All right, I'll show you one more object you could look at through binoculars or a small telescope. So let me go back to the simulator and show you where it is in the sky. So we're going to zoom out. Now, both M44 and M67 are what we call open star clusters or galactic star clusters. We see them more or less in the plane of the galaxy. And in my simulator here, you can see that all of these little circles with yellow dots around them, these are open star clusters. That's the symbol in the simulator for an open star cluster. If I look over in the east, I see a star cluster over here marked by a circle with a plus. And these are what are called globular star clusters. This one over here in Hercules, which is M13, is a really nice one. I can zoom in on it to show you what it looks like in the simulator. Whoops, there it is. It's a little bit weird because it's got some star. Well, you can see what it looks like. So unlike an open star cluster, there are many, many more stars. It's quite a bit further away because these star clusters are up in the halo of the Milky Way rather than down here in the plane of the Milky Way with us. So they're much further away, they're much dimmer, but they do contain many more stars. Now, in my backyard, I have a problem of there being a lot of trees around my backyard. Actually, not so much a problem, I like it. But for doing astronomy, it's a problem. I can only really look directly overhead. So last night when I was doing my tests, I looked to see, well, are there any globular clusters I could look at? And I went to look at this one called M3, Messier number 3. So I'll zoom in on it a little bit here and kind of see what it looks like there. And I'll show you the picture that I took last night. All right, here's M3, 20-second exposure from my backyard in the suburbs of New Haven with a little 8-inch telescope without really being properly calibrated. So not a great picture, but not a terrible picture either. I'm actually pretty happy with how this turned out. So many, many more stars, hundreds of thousands of stars. And you can see the brightest stars in the star cluster are actually reddish in color. They've got kind of a reddish hue to them relative to the other stars kind of around them. So probably red giants. This is a very old star cluster. In fact, globular clusters contain some of the oldest stars in the galaxies. They're interesting to study for that purpose. All right, let's see if there are any other questions. See if there's anything else I want to point out in the simulator. I don't think so. So any night it's clear this week, go outside, do some stargazing. You know, it's harder to do stargazing when the moon is full, of course, because you get a lot of light pollution from the moon. So the fainter constellations are really hard to see. The fainter meteors and a meteor shower are harder to see. One thing I think is nice about being outside when the moon is full, it's less about looking up at the sky and stargazing, but looking around at nature and kind of enjoying the moonlight that you have at night on the full moon. Of course, the full moon is up all night when it's full. The full moon rises at sunset and the full moon sets at sunrise. So you have the full moon up all night. So when I used to live in New Mexico, a popular thing to do when the moon was full was to go out on a desert hike, go hiking in the desert when the moon is full. And you almost forget, because your eye gets adapted to the dark, you almost forget that it's the middle of the night because the moon is so bright. But I would find myself, when I did that, thinking about humans in history and our connection to the moon, how we had a much stronger connection in the past. And people would really want to know what the phase of the moon was going to be, because it's so different going outside at night when all you have is fire to provide illumination at night. So get outside this week, enjoy the full moon. Try to find these bright stars. If you have a pair of binoculars, look for the Beehive cluster, look for the M3 cluster, and maybe even look for the Hercules star cluster down here, all of which you can see with binoculars. All right, Sam is patiently waiting to talk about exoplanets. So let me switch over to Sam. All right. Starting over, we were talking about telescopes. Well, let's skip that part and go right to talking about exoplanets. So I was saying that people may not know that we have some really advanced research in exoplanet discovery and research and learning all we can about planets around other stars at Yale. So can you tell us a little bit about this discovery first?
Sure. I am a second-year graduate student working for Professor Deborah Fisher in Yale's astronomy department. Her group, Professor Fisher's group, recently commissioned a new instrument, a new spectrograph called EXRES, which is installed on a telescope in Arizona. And EXRES's main goal is to look for small planets orbiting other stars. So these are exoplanets, any planet that orbits a star other than the sun. One of the other types of science that you can do, other than just looking for new planets, is also to study the atmospheres of some other types of planets. And the recent result that we've come out with is actually seeing what's in the atmosphere of one of these planets orbiting another star. And that's what I have to share tonight. I've got a very short slide deck.
Cool. Okay. All right.
I can go through.
Yes, academics always have to have slides, but that's good. You made these slides. I noticed that the press release image, the main press release, had your name on it, so that's great.
Thank you. Yeah, I tried to make a couple graphics for the press release, including the main image of the hot Jupiter. It's called the exoplanet itself, right next to the host star. So this is just, of course, a rendering, just an illustration of what it might sort of look like. Of course, if you were right there, you'd be very much blinded by the star itself. It's so bright, but it's sort of the best guess we have as to what the planet and star look like. So. Let's see. Could I go ahead and share my screen?
Yeah, go ahead.
Would that be all right? All right.
Hopefully that won't break anything, but I don't think so.
All right. Let's see. That's coming through all right?
Yeah, I'll move it over a little bit, but there we go. So actually, I wanted to ask you about this planet name, Mascara. So that's like a word that means mask, right? Astronomers love their forced acronyms, I know.
Oh yeah, absolutely. I don't know what this acronym stands for exactly, but what I do know is that it's named after the survey that found the planet. So certain groups have telescopes dedicated to trying to find exoplanets orbiting other stars. And what often happens is if they discover an exoplanet, then they'll build up a catalog of exoplanets that are named after that survey. And so this was the Mascara survey.
Great. So not a planet that you discovered, although certainly the Yale people have discovered lots of planets, but one that you've discovered something about.
Absolutely.
Okay.
So I'll just sort of go into a short presentation about it. So again, Mascara 2b is an exoplanet. It's very far away. So we have some understanding of what planets are like in our own solar system. Including Mercury, Venus, Earth, Jupiter, and the sorts. But there's this whole population of exoplanets around other stars. And most stars that we see in the night sky actually have planets orbiting them. And some are very much like the planets that we have in our solar system, whereas others, like Mascara 2b, are unlike anything we have and are completely different. And that's part of what makes Mascara 2b very interesting to study. So a brief bit about Mascara 2b. So it's 140 parsecs away, and parsecs is a unit that astronomers like to use. This translates into over 2 quadrillion miles away. So again, these are huge distances we're talking about when we talk about exoplanets orbiting other stars in the night sky. The star is a bit different than the sun. It's much hotter and it shines much brighter. It's about 15 times brighter than the sun. And the planet itself is about the size of Jupiter, a little bit larger actually. And Jupiter is a very big planet, and it's mostly made up of gas, and unlike Earth, which has a rocky interior. And it's so large that you could fit probably thousands of Earths inside this planet, Mascara 2b. And another thing that makes this planet interesting is that even though it's as big as Jupiter, it actually orbits much closer than Jupiter does in our own solar system, much closer than Earth too, and actually even closer than Mercury. It orbits right next to its host star. And as a result, it's very hot. And because it's also the size of Jupiter and made up of gas, these types of planets are called hot Jupiters. And that's what Mascara 2b falls into the category of. And another thing that makes hot Jupiters as a population interesting, and Mascara 2b as an example, is that these types of planets are tidally locked. And that means that the same face of the planet is always facing the star. So one analogy would be that we always see the same side of the moon. Even though the moon goes through different phases, we're always looking at the same craters and the same features because the moon is rotating as it orbits around the Earth. Mascara 2b is doing the same thing with its host star. As Mascara 2b orbits around the star, it's also turning slightly to keep the same face facing the host star. So that one side that's facing the host star, it's perpetually daytime, and it can get very hot, and you can get temperatures of a few thousand degrees, which can make for some interesting weather and effects and things. Let's see. So I'll talk briefly about how you study an exoplanet atmosphere. Exoplanets and their host stars are very far away, and they're very hard to see. In fact, in most cases, you can't even see the exoplanet through a telescope. You have to rely on some other means just because it's so small and so dim compared to its star. So instead of trying to look at photos, what astronomers tend to use is this method called spectroscopy and instruments called spectrographs that measure not just the picture and not just the total light that you get, but actually the spectrum of colors that you see when you look at the star and planet combined. And spectrographs work just like a prism. If you've ever shined a flashlight through a prism and you get a rainbow on the other side, or just like rain droplets, which project a rainbow after a storm. And these colors, all of the colors that you get when you break up the light into its components, these colors contain important information about the system that let you measure a host of physical properties, like what it's made of, how hot it is, these sorts of things. And so what we do to measure the atmosphere of Mascara 2b is we wait for it to transit its host star. So here's a short demonstration I'm about to play where the planet is going to pass in front of its star. Whoops. Yeah, there you go. And you'll notice on the bottom right, as the planet's in front of the host star, you get these dark bands at very specific colors.
Yeah, so I always feel like it's important for us to point out that like that picture is what's happening, but the spectrum is what we see, is what you're measuring. Like we can't really see the star or the planet, but we infer its presence based on the star dimming, and then you're talking about the atmosphere based on the spectrum.
Exactly. We can't actually see the planet itself in front of the star, but what we see are these colors that I've projected onto the right-hand side of the screen now. And what we see is that when the planet is in front of the star, certain colors end up being dimmer than other colors. Does that seem reasonable?
Yeah, Sam, I'm going to try and put your video up here so we can see. There we go. That's a little bit better.
Okay, great. And so, as I said, when it passes in front of its host star, it blocks out specific colors. And every gas, whether it's atomic or a molecule, it can be the oxygen we breathe, it can be helium, ozone, carbon dioxide, all of these things can block out specific wavelengths of light, specific colors of light. And the bands that we get, so those colors which are blocked out a bit extra by the atmosphere, are determined by what is inside the atmosphere. So what kinds of gases are inside of there. And when we compare the colors that we observe when the planet is not in front of the star to when it is in front of the star, we can tell what the atmosphere is made of by what colors are blocked out. So I think maybe one analogy is that, if these colors are like notes on a piano, when we're looking at the star, we're hearing all the keys played at once. And then when the planet passes in front of the star, it's almost as if you're letting go of a few specific keys. And if you have a highly trained ear, then you can hear which keys are missing. And that's effectively what a spectrograph does for this type of science. And you can figure out the types of atoms, the types of molecules that are in the atmosphere, how fast they're moving, and the pressures in the atmosphere. So that was a bit about the methodology, and now I'll share with you what we found. So when you make these measurements, you're effectively seeing what the weather is like on this exoplanet, what's going on inside its atmosphere. And through a large collaboration, we just published a paper on our findings. So for starters, we talked about how this planet is extremely hot. It's hotter than pretty much anything in our own solar system. And because of that, the temperatures are high enough to actually vaporize metals. So you can imagine iron, sodium, magnesium. These are all things that we were finding. Chromium. These are all metals that would normally exist as solids at room temperature, or if you were to hold one outside. But it's so hot on Mascara 2b that we're actually finding these metals vaporized in its atmosphere. And a couple of them hadn't been detected before in this planet. Magnesium and chromium are new ones that we found. Again, these are in gaseous form, and a couple of them are even ionized. It's so hot. So it's hot enough to actually strip the electrons off these metal atoms. We can tell how fast they're moving as well. And when we do that, we measure speeds that are over 10,000 miles an hour. So these are, again, very extreme weather conditions that you'd never see on a planet like Earth that's so small and far away from its star. But once you get to huge gas giants right next to their host star, you can get extreme weather patterns like this. And something else that we saw a hint of, not a really strong signal, but a bit weaker of a signal, is that we measured different chemistry in the morning and evening sides of the planet. So what that means is that from our point of view, there's one side of the planet that's rotating into view and one side of the planet that's rotating away from the star. And by looking at those two edges, which correspond to the evening on the planet on one side and the morning of the planet on the other side, we actually see different amounts of iron. So
That's
we see
amazing. Has that ever anything like that been seen before? Because that's a really amazing result.
So something like that just came out recently about another planet called WASP 76b. And it's a bit of a stronger signal there, but we're kind of corroborating what we found against that, which helps give some validation that this is an effect that can take place. And the interpretation here is that if you're finding iron vapor on one side, which then gets pushed into the nighttime on the planet, and then you're not finding it on the other side, where did the iron go? And what we think is happening is that it's cold enough on the night side of the planet that the iron condenses out of its vapor form into a solid, just as you would have, water vapor condensing into rain or snow. So on this planet, you might have iron vapor condensing into shards of solid iron that rain from the sky. So that's
Cool.
That's one interpretation of what's going on here. So these are sort of the main results that we found in the planet. So just looking forward a bit, I think this type of work is very useful for understanding this very bizarre category of planets called hot Jupiters, but it's also applicable for future telescopes and instruments that are coming in the future. And hopefully, eventually, what we'll be able to do is look at the atmospheres of even smaller planets that might be more Earth-like. And that's kind of a long-term goal of sort of atmospheric sciences, to look at smaller and smaller planets and thinner atmospheres for interesting molecules or compounds and understand what's going on there. Here I have a photo of myself in the middle, and then a colleague of mine, Joel, and then my supervisor, Professor Deborah Fisher, when we were out in Flagstaff, Arizona recently. Again, this new instrument that we've been using is named EXRES, and it's installed on this telescope, which is the Lowell Discovery Telescope. It's 4 meters, so that means the mirror on the back of it is 4 meters wide. It's huge, and you need a lot of mechanical structures to support that kind of an aperture. And you can see for scale some people in front of the telescope. And again, we're just like I mean, we're really excited for this cool discovery about the atmosphere of this planet. And then as well, that this is one of the first science results that has been produced by EXRES, which Professor Fisher and her team have spent a long time and a lot of hard work working on. And as I mentioned a bit earlier, EXRES's main goal is to find small planets as opposed to measuring their atmospheres. And it turns out that measuring the atmospheres of these large exoplanets involves the same techniques and can make use of the high fidelity instrument in the same way. And so what we're hoping for is kind of this mix in the future of planet detections, which are on their way, and maybe some more characterizations too, looking at atmospheres. So yeah, I think
That's great.
kind of summarizes the results in the EXRES project. So.
Yeah, that was a really nice summary. Let's just jump in and ask a couple of questions. And if anyone has questions for Sam before he leaves, by all means, post them in the YouTube live chat, and he can see them, or I can ask him. There's a great YouTube video about astronomy at Yale that was made a few years ago, 4 or 5 years ago now. I'll post the link in the description, but it actually shows Professor Fisher's postdocs and team collaborators working on building this instrument. So you can actually see the results now from that instrument that was in that YouTube video that was made a couple of years ago. So that's really nice. I did want to ask, so studying the atmospheres of planets, that's not the main purpose of this instrument. I mean, right, this is meant to discover new planets that are lower mass. Is it that this is just a nice serendipitous result, or is this a side project for the instrument, something that you could do is study atmospheres of already known, already discovered exoplanets?
That's a great question. Yeah, so that is the case. So that EXRES's main goal is to look for smaller, lower mass planets. To look for planets requires a lot of observations over a long period of time, because the way that EXRES looks for planets involves seeing the planet throughout its entire orbit around its star. And if you're looking for something that's kind of like Earth, then you're going to need to collect data over many months or even years in some cases. The thing about transmission spectroscopy, which is the type of science that we did here to study this atmosphere, is that it can be done in a single night. You can collect it maybe a couple nights of data too if you'd like, but all you need is for the planet to pass in front of its star. And to do this kind of work, you also need a very good spectrograph that is called a high resolving power. So we looked at the spectrum of light, but the ability to distinguish one color, one shade of red from another shade of red, or one shade of blue from another shade of blue. That kind of power is only offered by so many instruments in the world, and EXRES is one of them. And EXRES has a lot of other features that make it a particularly precise and stable spectrograph that, in some sense, goes above and beyond what you need for atmospheric work, but again, is not offered by many instruments in the world. And so EXRES is a great instrument for this kind of work too.
Does all of the data from EXRES go to Yale? Or are there other collaborators that are using it for other things?
Yeah, we've got other collaborators right now. Mostly through schools that are part of the Lowell Discovery Telescope Consortium. And actually, there's even been other people using it for atmospheric work too. So, which has been pretty fun.
Collaborators.
Yeah, collaborators.
We're all working together.
Yeah.
Great. So again, if anyone has any questions, feel free to throw them out. Let's see. I see one question. If oxygen were to be detected in an exoplanet, might there be an indicator of plant life? Yeah, Sam, I wanted to ask you this. Is there life on Mascara 2b?
So for Mascara 2b, almost certainly not. There's definitely no type of life as we know it that could survive at these temperatures and this kind of harsh environment.
with raining iron, shards of iron.
Yeah, that's just like, yeah, it's not too healthy. The raining shards of iron. So,
Yeah, the
um,
whole tidally lock thing is problematic too.
absolutely.
Um,
Um,
but anyway, about that
but
specific question, do you think you could find would this instrument using this technique be able to find oxygen in the atmosphere of a
so
planet?
it's a really good question. And oxygen is very highly sought after because it has these, it's attributed to life, and it's attributed to biological processes. It's hard to get oxygen on its own unless you have a process like photosynthesis going on. Um, it would probably be beyond the reach of, I'd say, a lot of the ground-based observatories today to look for oxygen, especially on a smaller planet that was more Earth-like. Even if it was a little bit larger than Earth, it would still be very challenging to find oxygen. But there's designs for spectrographs on large telescopes that are coming up in the next decade or two that are designed in a similar way as EXRES. They're designed to be high resolving power, very precise, and on large telescopes that can collect a lot of light. And with those kinds of instruments, we might be able to try going after oxygen. And that might be one of our best bets for looking for plant-based life.
Plant-based, yeah, photosynthesis of some kind.
Yeah.
Yeah. Um, do you think there's life on other planets?
That's a great it's a great question, and it's a tough one. I I'd like to be optimistic. I think there's a lot of unknowns involved in that question, a lot of hard things that we don't have the answers to. But there's so many stars out there, and there's so many planets as we've you know recently come to learn.
Yeah.
So it's hard to know, but
Do you
I'd like to
think
be optimistic.
so if we were to find, if there is life on other planets, what do you think is the best way for us to find it? So wait for UFOs to land on the White House lawn, wait for
Yeah,
a
God.
signal from using a radio telescope sent from Vega or something,
Like,
or looking at the atmospheres of exoplanets with spectrographs.
reminds me of did you ever see Independence Day?
Yeah, yeah.
Yeah, that one. And then Contact, of course. Um, I think atmospheric spectroscopy is probably going to be one of the main ways of looking for life. I think because the distances are so great to these other systems, it'd be very hard to send a probe one way or another
Hmm.
to search for things or make contact. I think, the atmosphere itself is a very large thing on a planet. And if you can measure that with high precision, then um, then I think that's your best way of peering into whether or not there might be life on that planet. So I think this is probably one of the more promising avenues for doing that kind of work.
Yeah. Let's see, another question for you. What elements besides oxygen might be an indicator of life on an exoplanet?
Yep. So there's a few, and I don't know all of them off the top of my head. I know oxygen O2 is one, ozone O3 is another one. Methane is also a molecule that would be indicative of life. These are called biomarkers. Um, and there's other molecules that are associated with life, for example, carbon dioxide. But what becomes a bit tricky is that some of the molecules that are produced by life can also be produced in geological processes. So you might have gases that come out of volcanoes or these sorts of things. And you're looking for a set of molecules that would uniquely point towards life.
Hmm.
And that's a challenging set to come by. But oxygen, methane, and then I think also nitrous oxide maybe are some of the main ones.
Nitrous
Oxygen,
oxide.
yeah,
Interesting.
net, oxygen containing molecules in
Yeah.
particular are.
Yeah, well, oxygen is so reactive that, I mean, the Earth, when the Earth first formed, there was no oxygen. It's so reactive that it's hard to see how it could stick around without, without something like life keeping it going.
Exactly.
Let's see, if the same side of the planet always faces the star, when the iron turns to metal, when does it vaporize again? Yeah, good question. So what's the seasonal cycle? How does the iron condense and vaporize? That's a great question.
Oh boy. Yeah, I'll try to answer that as best as I can. I don't know the specifics because we haven't done a detailed sort of modeling of the actual flow of gas on the planet. But what effectively happens is that the gas from the day side gets blown by this intense radiation from the star, it gets blown to the other side of the planet, around the planet to the night side. And I don't know how long it's on the night side before it wraps around. I don't have that number off the top of my head. But once it reaches the other side and comes back into daylight, then temperatures get hot enough again that it can vaporize. And
yeah, that makes sense. So, we think about it's hot during the day and cold at night. But, if it's always day and always night in some place, you're going to have these really strong winds that are going to push things around. That makes sense.
Absolutely. Yeah. Absolutely.
All right. Well, thanks so much for coming on to talk with us about this. And congratulations on this nice result.
Thank you. Thank you.
And what are you working on next? What's your next project?
We're doing a little bit more atmospheric work with EXRES, of course, and I'm also helping Professor Fisher with the main planet detection survey too. So I'm contributing to that. I also observe. So recently the observatory has been shut down because of the outbreak, but I've been observing remotely a bit, as well as occasional trips to Arizona. And I've also got a short side project that I've been doing with Professor Greg Laughlin on studying meteorites from other planets. So actually, I was a bit intrigued by this question that you had a bit earlier on meteorites coming from the moon. We're doing a theoretical study on the transfer of meteorites in the solar system right now. So.
Oh, great. So you probably know more about it than I do. I mean, it takes hundreds of millions of years for the transfer to happen. But I mean, the little I know about it is that it's much more common than you'd think. Is that right? Like, basically, we're constantly sharing germs. All the planets are sharing material with each other.
Absolutely. Yeah. And actually, it's something that still wows me is that you've got pieces of Mars on Earth from these processes.
Yeah, pieces of Mars, pieces of Mercury. Probably we've got pieces of Pluto somewhere.
Yeah, probably. So, it's really incredible. So, anyways, Professor Faison, thank you for hosting me tonight. This has been great.
Okay. Yeah. Thanks again.
And thank you for the great questions too.
Wait, what was that?
Yeah. And thank you for the great questions too, you and the.
Yes, thanks for everyone watching for the questions.
Yep.
And I'll post a link to the press release and also that video that I mentioned in the description. All right. Bye. Bye, Sam.
All right. Thank you. Take care.
Bye.
Bye-bye.
Okay, so I am going to see if it's clear. Let's see what the weather says. And it's getting a little bit late, so if I don't get an image from the telescope instantly, I may not spend a lot of time trying to point it. Let's see what we see out there. All right, so there's my my little telescope. Starting to get dark out there. Let's see if I'm still connected to it from earlier. I'll try to point at the star Pollux. So you should see the telescope move from the live camera as I move this around. All right. So what's going on here is I've got my laptop computer outside connected to the telescope, and I'm controlling it remotely from my office. And I can bring up a map of the sky here. and basically command the telescope to point at anything. And this is very similar to the way that we do observing for our labs and advanced projects for classes at the Leitner Observatory. But this mount is old and it's portable, so it's not quite as robust as the better mount that we use with the 16-inch telescope. But it worked last night, so it might work tonight. So I need to go make sure the telescope's pointed at Pollux, and I need to turn on the camera so that I can take a picture. And I'm willing to spend 5 or 10 minutes on it to see if it works. And if not, then maybe I will call it a night. So one of the things that I can do, I know my microphone doesn't, my Bluetooth microphone doesn't work all the way down in the garden. But what I can do is I can turn on the audio from the security cam, and you might hear me out there moving around. You might hear the telescope moving around. All right, I'm back. So while I was out there, you may have noticed me. I first pointed at Pollux and couldn't really get a good image, but I knew it was nearby. And then I pointed at Regulus, and this picture that I just took is just a very quick image, very quick picture of the star Regulus, which is that bright star in Leo. So not too bad. It's not perfectly centered, and it's kind of a noisy image. There's Regulus. It has a companion right next to it. Now this is a color camera, but it's not showing up in color because I'm not using the the filter information to show that. There's a way that I could do that, but sort of for a quick image, this is what it looks like. The telescope that Sam was talking about that they use in Arizona is a 4-meter diameter telescope. And this telescope that I'm using is an 8-inch diameter telescope. So instead of 4 meters, it's 20 centimeters in diameter. This star, by the way, I looked it up. The star with this planet is in the constellation of Cygnus, so it's not up to night. But it is a fairly bright star. It's a star you could see with a small telescope. So it's kind of interesting. I kind of want to, in this next summer, I want to go look at it and think about the shards of iron falling down from the sky. It kind of makes you wonder what's happening on planets around other stars as well. Anyway, what should we look at? Should we go take a picture of M44? Let's see if we can find it. So I'm up here in my office and I'm gonna try to do something that always amazes me. I'm gonna try to move the telescope from here. Really should try to get that center better, but that's okay. And I'm gonna move to M44, which is the Beehive star cluster. And we'll see if we can find it, and we'll see how good our focus is tonight. Live backyard observing. Okay, here we go. We're going to move the telescope. I'm going to click slew, which is astronomy talk for move the telescope, and you should see it move there in the camera. There it goes. I'm not using a fancy digital detector here, a fancy camera. I'm just using the same SLR that I used last week. All right, let's see if there's anything there. Let's take a picture. Live observing for Leitner Public Night. We'll take a 3-second exposure. And it takes a second for it to download. There it is. There's the star cluster. So again, it's not in color. There's a little bit of conversion I have to do to get it in color. I can adjust the brightness and contrast a little bit. It's also not in perfect focus. This is something else I'd have to do, is go down and zoom in on a little bit here. So you can see the stars aren't perfectly sharp. They're little blobs. And there's some I noticed this last night when I was doing some tests with this telescope, was that the mirror is a little bit out of alignment, so it makes the stars a little bit not round. But yeah, I'm pretty happy with that. There's the M13 star cluster that I was looking at last night and that we looked at last week. Beautiful target for binoculars, great first target to look at if you're interested in getting into finding star clusters with your binoculars or your small telescope. Actually, I saw there was an earlier question in the chat about telescopes. I'm not sure Richard is still on, but a quick question about what's a good telescope to see planets with. Because the telescope I have, you can't see planets. Well, you should be able to see planets with almost any telescope. You may not see them at high magnification. So you may need to get some training with the telescope, talk to some amateur astronomers about how to get them centered and in focus and what the best eyepiece is. You know, the telescope that I talked about last week that I used for live streaming last week, the Meade 90 millimeter, is a great option. By the way, I can tell that the stars are in imperfect focus because do you see how that one's a little donut right there? So when the stars aren't in perfect focus, they end up kind of looking like little donuts because that's what the telescope looks like. The front of the telescope looks like. Let's see. While I'm talking, I'll bring up my video just so you can see me here. Okay. The moon, well, see, the moon is, we could try the moon. It's very bright. It's probably behind my house at the moment, but let's take a look. All right. Here to the picture of the M44 cluster. Here's the moon down there. So I think maybe what we'll do is we'll flip the telescope over and you'll see it move over to that part of the sky. And we'll see if the house is in the way or not. I think it's probably going to be in the way. Someone's requesting M51. M51 is definitely in the trees. M51 is a really nice galaxy, which is over in this part. It's kind of in the handle of the Big Dipper. And so it's definitely in the trees from my house. But I promise, once I get access to the Leitner Observatory, if I'm still doing live streams, if we're not open to the public, which is probably going to be a while, to be honest, right? We're going to have museums and campuses closed certainly for the rest of the summer, and who knows when we'll be able to open up entirely to the public. Maybe in limited ways we'll be able to open up sooner. But I'm hoping to get access to the observatory sooner because I would be the only person there. And I'm going to be teaching a summer research program for high school students online using the telescopes at the observatory. So I have to get in there and start setting up the equipment for remote observing and getting ready for that. So I hope I'll have access to the observatory for public night in a couple of weeks, in which case I can do much more interesting telescope observing than what I can do from my backyard. But let's try to point at the moon and we'll see if anything's in the way. The other interesting targets, by the way, that are sort of out kind of in this part of the sky where I can see are galaxies. There are a lot of galaxies in this part of the sky. The Virgo cluster galaxies are all right about here, and the Coma cluster galaxies are here, and the M51 and M101 galaxies are up here. So there's this whole kind of row of galaxies across the sky that are associated with the Virgo cluster and the Virgo supercluster. That globular cluster that I took a picture of last night is over in this part of the sky. And so actually I could point the telescope at that. I know that that's feasible to look at. So what the telescope's going to do, you can see it in the camera feed, is that the moon's on the other side of the sky. So the telescope's going to point to the north and then swing around to the west and then come back down and point in the direction of the moon. So it may well actually be pointing right up into my office window. So I could potentially go stand in the window over there and wave, and that's what you get a picture of. The yellow bullseye that you see on the screen is where the telescope is moving. That's where it's pointed currently. So it's kind of swinging around the north where the trees are, and then it's going to come back down and point to the kind of southeast where the moon is. This telescope mount is probably about 15 years old. It's a Losmandy G11 Mount, and these Losmandy mounts are very sturdy, but the G11 mounts are not quite as sturdy as the G8 mounts, which is what we mostly use at Leitner. But this one has a computer control, so I can control it from somewhere else. And my security camera has an infrared light on it that's lighting up things at night, so that's why you can see the mount and the telescope reflecting light. All right, let's try to take a picture of the moon. So we'll take a really short exposure. Let's see what we see. It was nice last week, yeah, so I don't see anything there. That's basically an obstruction. That's what it looks like when it's cloudy. It was nice last week when we had the first quarter moon, which is really high in the sky, so it was well placed for me to see it from my backyard, but have a lot of limitations. Well, it was worth a try, and now we're getting up to 9 o'clock, so I think I'll stop there and promise to do a more interesting live stream from telescopes when I have access to the Leitner Observatory in a few weeks. Well, thanks to everyone for your attention and for watching the stream and throwing your questions out for Sam. Next time I'll show a planetarium show, I welcome questions about the Leitner Observatory or about astronomy news, anything like that. The summer program that we're going to be starting in a couple of weeks, something that I'm very proud of and very interested in running. So I'm glad we're going to be able to do it online, even if we can't do it in person. But you can find out about the Leitner Observatory at our website, which is leitnerobservatory.yale.edu. So Leitner is Leitner, leitnerobservatory.yale.edu. And you can send us an email at the email address info@leitnerobservatory.org. And you can contact me, Michael Faison. You can send me an email at my email address, which is michael.faison, Faison, at yale.edu. And I'll see you next time. Thanks for watching. Bye, everyone.